And today we're looking at electromagnetic induction. We're not going to produce a large current, but always with any electrical experiments, have caution with electricity. This is the equipment that we're going to set up. A demonstration ammeter there, the coil, the white plastic holder, it's got some insulated wire in it. I'm going to have a magnet with connecting our wires, alligator clips, and you'll need some scissors. And so the first thing you're going to do is strip the end of the each end of the coil of wire, only about 1 inch, 2.5 centimeters, and then connect the alligator clips to this stripped portion. It's important that the insulated part is in the coil. And then you can check the polarity of the magnet with a gimbaled compass needle. And here we've got the blue south end of the lower magnet, and you might just be able to see the red end on the gimbal. And here are the circuits. On the left you've got the actual one. You can barely see the wire going to the alligator clips, and a regular circuit diagram on the right side. And to remember, there is no power supply. The purpose of the experiment is going to be to produce a current. So we're going to introduce a magnet and place a magnet into the center of the coil, moving it forwards, moving it backwards. The idea is it's not stationary, it's all about moving the magnetic field in the electric field. And then you're going to pull it out. And you can do that several times and watch what happens on the ammeter that is connected there. And so the apparatus here we're going to explain in terms of Fleming's left-hand rule. And it's been set up in this diagram so that the field direction is that of the magnetic field, and then you've got the second finger pointing downwards, which is the direction of the conventional current, and your thumb is the motion, so that's where the direction of movement is going to be. And now you're going to look at the actual lab and note carefully on the ammeter and what actually causes.
But if you pull it out, something good happens. Notice you push it in one way, pull it out the other. Now you're familiar with this to some extent. You haven't really got a handle on it yet, but it's not bad. So the question is, and I sort of set this a couple of days ago and we didn't really get to finish it because the bell went. As I push it in, as I pull it out, suppose I want to create more current. What would I have to do? There's a couple of things. Move it faster, right. So if you move it slowly, you can see it's a bit dull. But if you move it fast, you get far more. So rapid motion is important. What you're really doing with these wires is cutting flux. So if you imagine the flux coming out of here, the most magnetic field lines that we agreed don't really exist. But what did you say about the, oh sorry, you're chewing sweets.
It's like a
You've changed your tune. What did she say? Do you remember?
representation.
Yeah, it's a geometric representation of the shape of a vector field, so it gives some indication of its strength and direction. But if you have one wire, not much register. So the deal is more turns. So more turns, faster motion, and that's really it. Okay? Now, as I push it in, let's assume this is a north end. Now I had that thing set up the other day that rotated. As I bring it towards, what gets created over here? A north or a south as I'm moving it in? This is a north end. I bring the north end. Oh dear, oh dear, oh dear. Now why can it not be a south? Think. This is difficult. well, it's not difficult, but it's a principle that you should know. It cannot be a south end which would attract it, right? Why must it repel it? Does this show a flow of energy? Is that what this really is measuring?
No, it's a difference, right?
I was hoping for the answer yes. But you know, hey, I'm okay to argue about it. If you make a current in here, which is what this is measuring, is current a kind of energy? Is kinetic energy of electrons, right? On its own, it would accelerate and rush towards there, and you have energy from nowhere. It doesn't work that way in the universe we live in. Someone's got to do some work to make that energy possible. So this repels. As you withdraw the north, are you still doing work?
Yes.
So it switches around the other way. So as you pull the north out, this will become a south, and that's where the current flow switches. Easy peasy?
And then, having seen a little bit of the video, solidify your knowledge. Why was the current produced? What happens if the north pole of the magnet is moved into the coil first? And thirdly, how could you alter the amount of current that is produced? Things to think about, things to answer. And many thanks to Mr. Godwin's 10th grade class and Team Science at Washington International School.